Welcome, and thank you for joining our discussion today on temperature instrumentation in the FCC. My name is Taylor Fama, and I'll be leading our discussion. For those of you who don't already know me, I am the Director of Temperature Instrumentation in the Western Hemisphere for Daily Thermetrics, and I've been with Daily since 2010. During my tenure, I've worked with a variety of operators, EPCs, and licensors across the globe in support of thermometry upgrade projects, and I look forward to bringing that experience to bear in our discussion today. Now, before we get into the details of today's topics, I'd like to give a brief company overview to give some context on who Daily Thermetrics is and what makes us qualified to speak to you today about these topics. Daily Thermetrics was founded in 1973 by Mr. Jeff Daly. The name Daly is indeed a family name, and to this day, we remain privately held and are currently led by our owner and CEO, Dr. Annabelle Daly. Our company is specifically focused on the design, manufacturing, and installation of temperature instrumentation for the downstream oil and gas industries. We are based in Houston, Texas, where we house our global manufacturing center and engineering hub. We do business on 6 continents and support the global process industries with direct regional support located all around the world. By maintaining such a precise focus over the course of decades, we have established a unique expertise in temperature instrumentation that provides our customers access to a partner that intimately knows their processes and challenges. The temperature measurement applications your team may see once every 4 to 5 years are applications we work on dozens of times per year, giving us fresh and constant insights to provide the latest industry recommendations to our clients. Our company is segmented into 4 distinct focus groups that support different critical areas of operation throughout a refinery. Each of these divisions is supported by its own specialized engineering team. First, our standard Thermowell and sensor team covers much of the traditional inline process measurement technologies. This covers thermocouples, RTDs, and Thermowells, including helical strake styles for vortex suppression, as well as hard face coatings, which will be an important topic of discussion for us today. Secondly, our vessel temperature measurement department. This group specializes in applications for profiling fixed bed hydroprocessing vessels like hydrotreaters and hydrocrackers, storage tanks, fractionation columns, and tubular reactors. This typically involves instrumentation categorized as multi-point thermocouples, which are commonly used in the FCC block for applications such as the cat feed hydrotreater and the FCC fractionator. Third, our surface temperature measurement department. This group is specifically focused on technologies to measure the skin temperature of vessels and piping. This includes the outer and inner surfaces of vessels and pipelines, and it also includes the measurement of heater tubes inside of fired equipment, such as charge heaters and boilers. These are highly engineered solutions that are built to accommodate extreme conditions, high temperatures, corrosive environments, and differential thermal expansion. Later in our talk today, we'll be outlining a surface temperature application at the Cyclone dip leg location that is unique to the FCC. Supporting all 3 of these groups is our Field Engineering Services division. This division is a dedicated team of field specialists that can help you with hands-on expertise at the site before, during, and post-installation. We have the ability to help with front-end walkdowns, troubleshooting and diagnostics, all the way through equipment redesign and turnkey installation of complex systems. Our turnkey offerings can completely outsource the installation process, including preparation, welding, inspection, etc., to help ensure a safe, efficient, and reliable installation of your temperature systems. Now, Daly's experience and reach stretches beyond just domestic operators and end users. While we have approvals and master service agreements in place around the world at the end user level, our regional support teams are positioned around the world to support our customers and their projects at all phases and in all locations. We work closely with EPCs both locally and globally, and work hand in hand with process licensors to innovate and refine thermocouple technology to meet the challenging needs of refining processes. No matter the location or scope of your project, we have the approval, experience, and presence to be a valuable project partner. Moving forward, I want to establish our agenda so we can set your expectations for the rest of the program. I want to focus on 3 main areas within the FCC. The first topic we're going to discuss is hard face thermowells. As we know, erosion is a challenge in the FCC, and there are a number of things from a thermowell standpoint that should be considered to optimize reliability in that process. Secondly, we're going to dig a little bit deeper into the application for hard face thermowells and take a look at the riser TI application, which can bring its own challenges in regards to installation and reliability. And third, we'll talk about the Cyclone exit legs, or dip legs, and introduce or reintroduce some technology that allows for points of measurement in locations you may not currently be monitoring with temperature. With that groundwork laid, let's take a look at our first topic, hard-face thermowells. Our first topic of discussion today is hard-face thermowells in the FCC. But before we get into the specifics of the FCC considerations, I'd like to lay a general foundation on thermowell design so that everyone in the audience has a good base understanding for us to build on. Thermowells are designed to house and protect temperature sensors. Typically, they're constructed of a piece of bar stock welded to a flange for connection to a pipeline or vessel, though they can use threaded connections, welded connections, and others. The bar stock is drilled to accept a temperature probe, and a threaded instrument connection on the back of the thermowell allows for a fitting to be used that can hold the sensor in positive contact with the tip of the thermowell, and in some cases, create a secondary process seal. This arrangement allows for the temperature sensor inside to be replaced while the unit is online in most cases. These thermowells can be inserted into a process pipeline, a vessel, a heater, anywhere a temperature measurement is required. The thermowell is pressure rated for the specific application in which it is installed, and its geometry is designed for the specific process conditions in the surface. Keep in mind, the thermowell itself is a process boundary, so special care must be taken in designing these assemblies to make sure the thermowells are suitable and reliable long-term. Erosive applications, however, present an additional set of challenges for thermowells and other pieces of equipment. Due to high-velocity particulate and catalyst, erosion of the equipment can lead to damage and compromise of anything in its path. In these cases, high-hardness materials and coatings are utilized to help minimize the impact of erosion on critical pieces of equipment. In the case of a thermowell and thermocouple, erosion and eventual failure can lead to a loss of a data point. But more importantly, it can also compromise the process boundary and lead to potential loss of containment. Because of this, the use of high-hardness coatings on thermowells is extremely common in any erosive environment. Important to our discussion today, there are nuances in the fabrication process that can have a direct impact on the reliability of these thermowells. Proper specification of the hard facing is a critical step in ensuring reliability of the thermowell, and today we will look at several key criteria to consider. First is the application method of the stellite coating to the base material of the thermowell. How is the coating bonded to the base material? Second is the coating length. How much coverage is actually needed? And third will be the coating thickness. First, looking at the application method, there are two main ways in which stellite coatings are applied to thermowells. The first of which is called spray infuse or thermal spray. This application method is fairly common and is easily identified out in the field by its dark gray color and sandpaper-like rough finish. The way that this application method is achieved is by using a powderized form of stellite that is then sprayed onto a superheated thermowell to bond the stellite to the base layer. As many of you will already know, this is the most inexpensive method for applying a stellite coating, and it comes with the associated drawbacks you would expect. In short, the bond between the coating and substrate produced by the spray infuse method is not as strong or effective as the bond produced by other methods. And this, in combination with its coating thickness limitations and the brittle nature of stellite itself, can lead to issues in the short term with this application method. If chipping or erosion begins to occur and exposes the base layer, the rest of the coating tends to flake off relatively quickly, and this will leave the base material exposed and in a very vulnerable position for quick erosion. For this reason, we typically recommend this type of coating only where erosion is expected to be minimal or where cost is a priority. For most all other situations, we recommend stellite coating via a welded overlay process. In this approach, the stellite coating is applied to the base material by either a TIG welding method using stellite weld rod or by a laser cladding process. This provides a superior metallurgical bond to the base material and eliminates the chipping and flaking phenomenon commonly seen with spray-infused coatings. In addition, the thermowell can be polished post-fabrication and post-coating, leaving a thermowell that is smoother, has better flow characteristics, and less susceptibility to corrosion and pitting. Process licensors typically specify this method, but if it is not explicitly stated in your specifications or in your request for bid, it is most common that you will receive spray-infused type thermowells due to their lower cost. Now, beyond selecting the appropriate application method, another important detail in the Thermowell design for hard facing is the length of the coating that is required. At a minimum, we would always recommend that a coating extend at least 1 inch into the nozzle so that the entire exposed length is protected by the Stellite hard facing plus a small buffer. If there is any uncertainty about the immersion length of the Thermowell, the entire Thermowell shank should be coated to prevent unnecessary exposure of the base material, which would quickly compromise the Thermowell. The third and final consideration I'd like to discuss is the thickness of the coating. Very commonly, 1/16 inch of Stellite on top of the base material is utilized. This is the minimum acceptable thickness for FCC service and is the maximum thickness available in many cases using the spray-infused coating method. While this thickness level may be sufficient for moderate severity applications, if we're dealing in a riser or in other places where we expect to see high velocity particulate, we always recommend an 1/8 inch coating thickness as a minimum in order to properly safeguard the Thermowell against erosion. As long as a strong metallurgical bond exists, the thickness of the coating has a direct impact on the amount of time the Thermowell can withstand erosion before exposing the base layer. All coating methods do have their limitations, but this metric can be an important factor in determining whether a Thermowell will survive a 5 to 6 year run cycle. Now, there are certain cases in which a Stellite coating may not be the best solution, especially in applications where we see extreme erosion. In these cases, no matter the method or the thickness, a simple coating isn't sufficient to withstand a long run without failure. And in these cases, we would recommend that you consider the use of a solid Stellite Thermowell. This greatly extends the service life of the Thermowell and the Thermocouple and can be constructed in a variety of ways, with either just the exposed tip of the Thermowell being made from Stellite or the entire shank. Coatings provide a great defense with the benefit of a lower cost due to the lower cost stainless steel base layer. But once the coating erodes, the base material degrades quickly. With no weaker base material below, solid Stellite variants resist erosion at the same level on day 1 as day 1000 until the entire wall thickness of the Thermowell erodes. This method has proven reliable between longer turnaround cycles without failure. Finding the right solution for your application is a combination of the strategies presented here and the historical knowledge and lesson learned from your own unit's operation. By collaborating with our team, we can help find the most reliable and cost-effective solution for your process. Now, before we switch gears, one last consideration I would like to mention is in regards to containment. As mentioned previously, these Thermowells are process boundaries. In the event that a Thermowell is breached due to erosion or other mechanical damage, process can potentially be vented to atmosphere. In most applications, these Thermowells are sealed on the back end with a compression fitting, but this can put operators and technicians in danger if they choose to replace one of these thermocouples without knowledge of the condition of the Thermowell inside. There are a number of ways this can be addressed, and our customers have used a myriad of options to do so. One common method would be to utilize a T-type fitting that would allow a technician to open the valve and see if anything bleeds out, alerting as to whether or not it's safe to proceed with the exchange of the temperature sensor. Another conservative approach is to assume that when the thermocouple fails, that the Thermowell has failed as well. In this scenario, a lubricated plug valve or shear valve can be mounted to the back of the Thermowell and can be used to cut the thermocouple and seal off the Thermowell so that no process can escape. This ensures a safe workspace around that instrument. All of these options are available from Daily Thermetrics, and depending on your procedures, we can help you design a solution that fits those needs. In closing, erosive applications provide some unique challenges when it comes to Thermowell design. If a hard face coating is deemed necessary for your application, always consider specifying the following details in addition to the hard face material type: application method, length of coating, and thickness of coating, as well as some consideration for what containment method is required at your facility. With that, we'll move on from this section and talk about a specific challenging application for hard face Thermowells in the riser. For this next section, we're going to look at a specific application within the FCC, one that pertains directly to the hard face coatings we just reviewed. One of the most extreme applications for Thermowells in this service is in the FCC riser. This is where we expect to see moderate to high velocities with a lot of particulate and catalyst fines. This is one location in which we very commonly see solid stellite tips utilized due to the rate of erosion. Erosion is so severe in some cases that we commonly also see deflector shields positioned below the thermowells to deflect the flow of catalyst around the thermowells to preserve them through the run. This application can present a number of challenges, specifically because of the position of the thermowell. In typical applications, a thermowell connection is external and exposed, making it easy to service and replace. This could be on a piece of pipe, the side of a vessel, or in the overhead of an FCC. However, in the case of the riser, in many situations, the thermowell is located inside the external vessel shell, where an internal riser would be located. This means that the thermocouple must enter from a connection point on the outside of the vessel and be routed upwards or downwards to the elevation where the riser thermowell is located before being seated in place. One of the conventional approaches we see for this application is the utilization of a guide pipe. This guide pipe serves as an internal thermocouple highway to route the probe from the outer vessel wall to the thermowell. This generally involves a number of bends to route the thermocouple to the correct thermowell elevation. And while this approach may be a sensible starting point for capturing this data, there are two critical drawbacks associated with the design that I'd like to walk us through. First, with two fixed points on this guide tube and the possibility of differential thermal expansion between the outer shell and the riser, there can be a lot of stress placed on that guide tube that can result in breakages. This can of course cause damage to the thermocouple inside, but it can also cause catalyst spillage from the riser into other areas of the reactor. The second major shortcoming of this approach is that in order to accommodate the bends in the guide pipe, a smaller diameter thermocouple must be used due to flexibility requirements. Typically, a 1/8 inch OD thermocouple is selected for this application, which is significantly smaller than the 1/4 inch thermocouples used widely throughout the plant. And with a smaller diameter thermocouple comes smaller conductor wires, which generally results in shortened instrument life. The good news, however, is that this guide pipe design is not the only approach available. Daily Thermetrics has developed and successfully implemented alternative solutions that effectively address the installation, mechanical, and instrument reliability concerns outlined previously. These solutions typically involve removing the guide pipe entirely and replacing it with a larger diameter, heavy wall thermocouple. The thermocouple will follow a similar path as the guide tube from the external connection to the thermowell, but to properly account for differential thermal expansion, special expansion bins can be built into the assembly to absorb any movement during startup and operation. The result is a much more robust thermocouple that offers better reliability, improved installation characteristics, and guaranteed positive contact with the thermowell tip to ensure the highest quality temperature data is captured and provided to the unit operators. However, if for any reason a guide pipe is a requirement for your arrangement, Daily Thermetrics does provide these instruments and does have the ability to build mock-up guide pipe arrangements to test the fit of the thermocouple and ensure the TC can be successfully installed before it's brought out into the field at your refinery. And with that, I'd like to move on to the final section of this program, which will focus on Cyclone exit legs. The last section of our discussion today will focus on a technology designed to help bring visibility into a critical area where many operators may not currently have any temperature data at all: Cyclone exit legs or dip legs. Monitoring the condition of the dip legs of your cyclones is a critical metric during startup. In this stage, it is possible to have moisture accumulation in the cyclone dip legs, and if catalyst is injected when enough moisture is present, it can cause clumping of catalyst and potentially clog or block the dip legs. At a minimum, this can result in delay and inefficiency, but in the worst case of a total blockage, dip legs can and have melted down. By monitoring the temperature of the dip legs during this startup procedure, information can be gathered about the current condition to ensure that this situation can be avoided. So how do we actually capture that data? To do this, Daily Thermetrics offers a technology comprised of multiple thermocouples that enter through a single nozzle on the exterior of the vessel. Each thermocouple is then routed internally to the dip legs, where it is welded at a position of interest. This then gives long-term, accurate trending data on the condition of the cyclone dip legs that can be utilized during startup, but can also be utilized for comparative analysis throughout the run. Now, there are a few really important design considerations for these types of assemblies, stemming from the fact that, similar to the riser application, there's a possibility of differential thermal expansion between the entry point of these thermocouples and the location in which they're welded. In order to safely accommodate this movement, special expansion loops and thermocouple routing patterns must be implemented. In fact, each of these thermocouple assemblies is custom designed to the specific dimensions and unique expansion characteristics of your FCC unit. And with decades of experience in this exact application, our engineering team makes this process incredibly straightforward and light duty for your team. In terms of implementation strategies, these instruments can be retrofitted to existing FCCs, and we commonly see them implemented during head replacement and cyclone replacement projects. In any of these cases, we strongly recommend that the installation process be supervised by a Daily Thermetrics field team that can provide welding, inspection, and project management services to ensure that these thermocouple assemblies are installed correctly, efficiently, and safely. Cyclone dip leg temperature monitoring is a very unique application that nicely showcases our ability to bring value and support projects from conceptual design phase all the way through product installation, unit commissioning, and beyond. With an expert supply partner, capturing this data is a simple and straightforward way to better monitor and safeguard your assets, especially during unit startup. With that, I'd like to conclude our program with a few closing remarks. Wrapping up our discussion for today, the FCC presents some very unique challenges for temperature instrumentation as well as other equipment. Through decades of experience and collaboration with operators, Daily Thermetrics has developed improvements, modifications, and new designs to strengthen the reliability, efficiency, and safety of your operation. We would very much look forward to being a partner with you on your next project, no matter the scale. Whether that be a turnaround, a revamp project, or even a grassroots unit, our team has the ability and the reach to support you at all levels of these initiatives. Finally, I want to thank you for your time and attention today, and I'd like to end with a question for you. What temperature-related challenges are you currently facing in your FCC unit, and how can we best engage with you to implement effective, long-term solutions? We'd love to hear from you. If you have any questions or comments, or if you'd like additional information about our company and products, please contact your Daily Thermetrics representative or reach out to us at sales@dailyinst.com.